In this video, I am focused on velocity vectors and the concept of relative velocity. This is the last of 7 videos in my Unit 2 titled Kinematics. If you want to practice what is covered in this video, then check out the video description. You can find a link to my worksheet 2.07 as well as video answers for each problem. Let's start with velocity vector addition. If there is more than one factor for an object's velocity, then vector addition can help turn the individual factors into a total or net velocity value. The first example is a swimmer in a river. Both the swimmer's paddling and the current in the river will contribute to the overall velocity of the person. The second example is an airplane flying through wind. Both the plane's engines and the wind will contribute to the overall velocity of the airplane. Here, looking at some basic examples, I'll use the swimmer and the river. It is known that the swimmer can paddle at 4 meters per second in still water, and the river carries a current of 3 meters per second to the east. In the first example, let's say the swimmer paddles in the direction of the river's current. I would add the vectors tip to tail. They point in the same direction, so the overall net velocity or vector would be 7 meters per second directed to the east. The next example will have the swimmer paddle against the river. We again add the vectors tip to tail, and the resultant vector or overall velocity is 1 meter per second to the west. The third example would be the swimmer paddling across the river or directing north. The river will carry the swimmer to the east, and now the tip to tail vector addition would be an angled vector directed north and east, and I would need to use trigonometry to find the magnitude of 5 meters per second, and then likely also the direction, which here would be 37 degrees east of north. So you may run into more situations than these 3. You always want to add your vectors tip to tail, as shown in the 3 examples above. Here is another example. We have a woman standing at the bank of a river. Directly across from her path is a location marked X, and her goal is to swim across the river and wind up at the X. Given her paddling speed, and also the current in the river, the question is, in which direction would she want to aim her paddling to wind up at the location marked X? Well, what she would not want to do is to aim her paddling directly at the X. Then the river will pull her to the east, and she'll wind up somewhere over here. So where should the swimmer aim? I think she should aim west of her intended target. I'm drawing a vector for her paddling that is directed north and west. And now when we add the river's effect, from the end of her vector, you can see that it will pull her back to the east and in line with the target. This has formed a right triangle. The goal is to solve for angle theta labeled in the triangle, which is relative to her direction in line with the x. I would perform the trigonometry, and it would produce a value of 34 degrees. I will state that as west of north, as she is directing her swim west of the target that is due north. So this example is a good one to visualize that we aren't always solving for the hypotenuse vector. Sometimes we know the hypotenuse vector and are solving for other things. One last example here for adding velocity vectors. I wanted to show one problem that got either length or time information involved. Here we have some information for length. The woman still swims at 2.5 meters per second. The river still carries a current of 1.4 meters per second to the east. But now we are also presented with the width of the river, given as 12 meters. You can see it with this marker. And if she aims her direction of paddling at the X, as discussed earlier, she will be pulled to the right and wind up some distance to the right from the target. And that's what we're solving for here. What horizontal distance will the river have pulled her when she reaches the other side of the river? To get started with the solution, let's first visualize the vector addition. She is aiming her paddling north. The river is pulling to the east. I'll start that at the end of the paddling vector. And you can see why she's going to wind up to the right of the target. These are all constant velocities. She is paddling at a constant velocity herself. The river carries a constant velocity current to the east. And so I'm referencing a constant velocity equation here at the top right. I think that will be useful to get these distance measurements involved. From there, let's talk about dimensions. I think we want to treat this as 2 independent dimensions, first in the north-south axis, and then second in the west and east axis. These dimensions are independent of each other, and so I want to treat them separately. Let's start with the north-south axis. The displacement is the width of the river, given as 12 meters. The only velocity in this dimension is her paddling at 2.5 meters per second. And now I can solve for the time that it takes her to cross the river using the constant velocity equation and winding up with a time of 4.8 seconds. Next, looking at the east-west axis, the displacement now is what we're solving for, variable d in the image. It is only the river that contributes to the velocity in this dimension, 1.4 meters per second, and exactly equal to the time that it takes her to cross the river is the time that the river will carry her to the east. And so I can use my constant velocity equation again and solve for the distance as 6.7 meters, and that will be the answer to this question. Last, looking at relative velocity. This is determining the velocity of an object with respect to an observer. But what makes these problems tricky is that the observer may or may not be stationary. Here is our first example. We have a person standing at rest near a cart that is moving at 3 meters per second to the east. Taking the point of view of the observer, it would appear that the cart is moving 3 meters per second away from him and directed to the east. So I would answer positive 3 meters per second as the velocity of the cart relative to the stationary observer. But now let's take the point of view of the cart. If I were riding on the cart and looking back at the person would appear to be drifting away from me or moving to the west. It would be no different than if the cart were at rest and the person were drifting 3 meters per second to the west, away from the cart. So I would answer negative 3 meters per second, or 3 meters per second to the west, for the velocity of the person relative to the cart. Here is example 2. We now have 2 moving carts. The blue cart is moving at 3 meters per second to the east, and the red cart is moving a little faster at 4 meters per second to the east. If I were taking the point of view of the blue cart, then the red cart would appear to be separating from me, but only by a small margin, which is the 1 meter per second difference in their velocities. This would be no different than if the blue cart were at rest and the red cart were moving at 1 meters per second to the east. So I would answer positive 1 meters per second, or 1 meters per second to the east, for the velocity of the red cart relative to the blue cart. But now taking the point of view of the red cart, if I were riding on the red cart and looking back at the blue cart would appear to be separating from me by a small amount, or moving to the west with a small velocity. It would appear no different than if I were at rest and the blue cart were moving with a velocity of 1 meter per second to the west. So I would answer negative 1 meter per second, or 1 meter per second to the west, as the velocity of the blue cart relative to the red cart. Here is our last example. We again have 2 moving carts, but now they are moving in opposite directions. Taking the point of view of the blue cart, which is helping to close the distance between the carts, the red cart would appear to be moving faster than it actually is. It would be no different than if the blue cart were at rest and the red cart were moving with a velocity of 7 meters per second to the west. So I would answer negative 7 meters per second, or 7 meters per second to the west, as the velocity of the red cart relative to the blue cart. But now taking the point of view of the red cart and looking back at the blue cart would appear to be approaching me with a velocity faster than it actually is traveling with, again because the red cart is helping to close that distance. It would be no different than if the red cart were at rest and the blue cart were moving with a velocity of 7 meters per second to the east. So the velocity of the blue cart relative to the red cart would be positive 7 meters per second, or 7 meters per second to the east. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.